All right, hello everybody. This is lesson 8.2, which is arithmetic sequences. So the three learning targets for this lesson, we're going to first determine if a sequence is arithmetic. So in lesson 8.1, we talked about sequences. Certain sequences that have a particular pattern are called arithmetic, and we're going to learn how to determine that. Next, we're going to find the nth term right here, and remember nth term is another way of saying explicit formula, so we're just going to find the explicit formula of an arithmetic sequence. And then we're going to look at the partial sum of an arithmetic sequence. So an arithmetic sequence is a sequence in which a fixed constant d is added to each term. So we're essentially just adding the same number over and over and over again. We actually saw some of those in lesson 8.1, just didn't specify them as arithmetic at the time, just a sequence. So now we're going to pay particular attention to these sequences where we're adding the same number every time. So here you can see I've got just generally written four terms of an or just four general terms: first term, second term, third term. And what we'd be doing is adding a particular number d to that first term to get the second term. Once we had the second term, we would add that same number d to get the third term, and once we had the third term, we would add that same value d to get to the fourth term. So that d here is what's referred to as a common difference. So if a sequence is arithmetic, it has a common difference that we can identify as the number being added to each term. So as an example here, 1, 6, 11, 16, we're adding 5, and then we add 5 to get to 11, and then we add 5 to get to 16, and we'd keep adding 5. So this sequence here, 1, 6, 11, 16, this is arithmetic. And we would say the common difference is 5. We have another one here, 7, 4, 1, -2. To go from 7 to 4, we're adding -3. To go from 4 to 1, we're adding -3. From 1 to -2, we're adding 3. So it looks like we're adding the same number every time again. And the number could be positive or negative, the common difference. So this one is also arithmetic. And the common difference is -3. So what you'll be practicing in the beginning of your homework is just determining if a sequence is arithmetic. So looking here at part A, go ahead and pause the video and determine if the given sequence is arithmetic. If it is, it means it would have a common difference. So for part A, from 4 to -1, we're adding 3, and then from 1 to -2, we add 3. From 2 to 5, we're adding 3. So since we're adding the same number every time, this does have a common difference, so it is arithmetic with a common difference of 3. Take a look at another one here. Go ahead and pause the video and try to determine if this sequence is arithmetic. What you hopefully found is from between the first and second term we're adding 3, but then we're adding 5, and then we add 7. Since we're not adding the same number every time, there's no common difference. Therefore, this is not arithmetic. So first learning target, pretty easy, just determining whether a sequence is arithmetic. Now the next learning target, finding the nth term, or coming up with an explicit formula. So let's get back to this notion then. Here I've got first term, second term, third term, fourth term. And we're going to say that this is an arithmetic sequence, meaning that we're adding d every time. And then from the second term to the third term, we're going to add d. So we're always adding a common difference. Now, first term is just equal to the first term. Second term, however, we can think of as the first term plus that common difference. So you see here I've written the second term a sub 2 is equal to the first term plus the common difference. Now, the third term we can think of as the first term plus 2 common differences, like that. A1 plus D plus D. And then we fix this here. Fourth term, if we wanted to look at the fourth term in relation to the first term, the fourth term is the first term if we add 3 common differences there. So fourth term is equal to a sub 1 plus d plus d plus d. What we're trying to establish here is a pattern. And we could say, just for the sake of completion, plus 0 d, since there isn't a d there. So now, what's an established pattern we can see? Each one of these starts with a sub 1, and then we're adding a certain number of d's. And what's the pattern with the number of d's that we're supposed to add? Here we're adding 0 d's, here we're adding 1, here we're adding 2, and here we're adding 3. What's the connection here? The number of d that is being added is always 1 less than the term, the number term. So for the first term, we don't add any common difference, obviously. But for the second term, we add 1 common difference. For the third term, we add 2 common differences. For the fourth term, we add 3 common differences. So the connection is we always add 1 less common differences than the actual number of the sequence. So the fourth term, for example, we know we would add 3 common differences. So the way to generalize this is the nth term, so any random term, not in any order, but just the nth term is equal to the first term, just like each one of these, always equal to the first term. And then we add a number of common differences that's 1 less than the term. For example, the fourth term, we added 3 common differences. 3 is 1 less than 4. So this is what's known as the nth term of an arithmetic sequence. We need to know the first term, and we need to know the common difference in order to write the nth term. So the way this would work then, as an example, find the nth term. We have, for part A, first term is 3, and the common difference is -2. So the nth term, a sub n, if we're following this formula right here, it would be 3, that's the first term, plus n minus 1 times the common difference times -2. And what we typically do now is rearrange this, distribute to get rid of the parentheses. So if I distribute the -2, I'm going to have the nth term a sub n is 3 plus -2n plus 2. Combining like terms, we have a sub n equals -2n plus 5. So this would be the nth term, or the explicit formula. You can see another example here, part B. They've given us part of the sequence now. Rather than specifying the first term and the common difference, they've just written out the first 4 terms of the sequence, and they're asking us to find the nth term. So we still need the same 2 pieces of information. We need the first term and the common difference. So obviously the first term is 12, and the common difference, so a sub 1 equals 12, and it looks like the common difference is -3. So to write the nth term, we use the formula a sub n equals the first term plus n minus 1 times the common difference. And then we simplify. So -3n plus 15. Now, I want to talk just for a minute before we get to the next example about a certain correlation between this and something that was brought up in the last lesson, lesson 8.1, where sequences can be related to functions, and in particular in 8.2, arithmetic sequences can be related to linear functions. When I say linear, meaning that their graphs are lines with slope and a y-intercept. So taking this sequence here, for example, 12, 9, 6, 3, let me get a little bit more space. So when n was 1, we had 12. When n was 2, we had 9. When n was 3, we had 6. If we were to translate that to a graph where n was our horizontal axis, a sub n is our vertical axis, then 1, 12, then we had 2, 9, 3, 6, 4, 3, let's see, that was 6, that was 9, that was 12, that was 3, okay. You can see that it's plotting a linear function, and typically the equation of linear functions is y equals mx plus b. That would be the equation of a linear function. Now, relate that to what we determined the explicit formula, or the nth term, was, -3n plus 15. Back to function notation, m typically represented the slope. The slope of this line is indeed -3. What does that correlate to with our explicit formula? It correlates to the common difference of -3. So the common difference of an arithmetic sequence can be related to the slope of a linear function. And then b, going back to function notation, b represents your y-intercept when x equals 0. There is no value for when n equals 0 in sequences. The very first term always starts with n equals 1. But if we wanted to try to imagine if there was a 0 term when n equals 0, so if we have 12, 9, 6, 3, this is when n equals 1, this is when n equals 2, this is when n equals 3. So if there was a term for which n equals 0 and it followed the same pattern, then that term would be 15. That's representative of a y-intercept if we're talking about linear functions. And that's represented here in our explicit formula. What I'm getting at is if we had our sequence written out, in order to quickly generate the explicit formula, we need to know the common difference, and it's -3. And then trying to relate this to y equals mx plus b form, this term here that we would be adding would be similar to a y-intercept, or a term when x equals 0, or when n equals 0. In this case, it would be 15. So it's going to be 15. That's maybe a quicker way to come up with an explicit formula for an arithmetic sequence than using this formula right here, which works. This formula works. It's just a matter of remembering the formula and going through and simplifying it. So for part C, we have an arithmetic sequence. We need to figure out the nth term. So a sub n, and if we're going to use the notion of relating this to a linear function, linear meaning slope and y-intercept, y equals mx plus b, the slope would be the common difference. So what is it we're adding to each term? And we're adding 7, so that would be our common difference, 7n. And then, so if we're thinking y equals mx plus b, the slope is like our common difference. The y-intercept, b in this case, would be a term that would exist if n equals 0, the term before the first term, if you will. And if we're adding 7 going in this direction, then we're subtracting 7 going in that direction. So subtracting 7 would mean we have -11 there. So our explicit formula is 7n minus 11. Now let's just see if that jives with our formula that we learned a moment ago. So it's the first term plus n minus 1 times the common difference. So the first term here was -4 plus n minus 1 times the common difference of 7. So this is -4 plus 7n minus 7, which is 7n minus 11. So it gives us the same result. So that's a quick introduction to finding the nth term of an arithmetic sequence. Now we have a little bit more advanced problem here to look at. So the 14th term of an arithmetic sequence is 39, and the 27th term is 65. We need to find the 50th term. And one of the keys here is that this is an arithmetic sequence, which means it has a common difference. And it can be represented using an explicit formula that resembles a linear function, y equals mx plus b. And that's the direction we're going to want to head here. In order to find the 50th term, we essentially need the explicit formula, or the nth term. We need the explicit formula, a sub n. So one thing we can do to help with this, since we need the explicit formula, is to think about this in terms of function notation. And I'm not talking about f of x, I'm talking input-output, or an input-output table. So it says the 14th term is 39. The 27th term is 65. So relating this back to what we did a moment ago to a function or a graph, let's see the 14th term. They said the 14th term was 39. And then by the time we got to the 27th term, it was way up here at 65. And the key was that it was arithmetic. It's a common difference, so it's going to increase at the same rate from there to there. So we have a linear function here. And a quick way of finding the slope of the linear function is rise over run, or the difference in y values here divided by the difference in x values. And the reason I'm focusing so much right now on slope, remember slope is synonymous in this case to the common difference. So if we can find the slope, we can find the common difference. The slope is the change in y values here divided by the change in x values here. So we could say the common difference is the change in y values divided by the change in x values. And the change in x is 13, the change in y, 65, that's 26. So the common difference is 2, meaning we're adding 2 to each term. If we had the 14th term as 39, so 39, and I know there was a bunch of terms before it, but the 14th term is 39, then the next one would be 41, then 43, so this is the 14th term, this is the 15th term, this is the 16th term. If we kept doing this all the way up to the 65th term, we know we would get, or to the 27th term, we know we'd get 65. So we have the common difference. In order to make our nth term, we need the first term if we're going to use that formula to find the nth term. So the common difference is 2. What's the first term? Well, we could backtrack and say, well, the 13th term is 37, 12th term is 35, the 11th term is 33, and keep going back down that way, which wouldn't be the most difficult thing in the world. What we could do also, going back to this formula, here, we could use this formula to solve for the first term by plugging in some known values. Using this bit of information, for example, when a sub n equals 39, we can solve for the first term, and the n value for 39 was 14. 14 minus 1 is 13. And I know the common difference is 2. So we have 39 equals a sub 1 plus 26. If you subtract 26, you get a sub 1 equals 13. So I know now the first term is 13. So now we can use that to figure out the nth term. We could use this formula here, or we could go straight into the y equals mx plus b notion and say, all right, a sub n, the slope is 2, or the common difference is 2, so it's 2n. And if there was a term in front of the first term, the 0 term, if you will, it would be 11, because that's 2 less than the first term. So there's our nth term, 2n plus 11. Now, the task was not simply to find the explicit formula or the nth term. The task was to find the 50th term. And now that we have the explicit formula, we can find the 50th term simply by plugging in a 50 right there for n. So the 50th term is 2 times 50, which is 100. 100 plus 11 is 111. So the 50th term there is 111. Okay. Now we're moving on to the final learning target, partial sum of an arithmetic sequence. So you can see I've got a partial sum here, and what it is, it's the sum of the first 100 positive integers. 1 plus 2 plus 3 plus all the way to 100. Now there's a story that goes along with this sum, and it's supposedly true. A few hundred years ago, and you might recognize the name Carl Friedrich Gauss. He's the one that we can thank for Gaussian elimination from the last unit. Anyway, when he was a young schoolboy, they say around 11 or 12, his teacher posed a question to the class, which was this exact question: find the sum of the first 100 positive integers. Now, it's probably the teacher needed a little bit of a break, assuming this would take the students a little bit of time, because back then, remember, there were no calculators. They would have had to add this by hand. So Mr. Gauss thought about this for a few minutes, came up with a quick way to solve this, put his paper on the teacher's desk, and totally blew his teacher away. So here's what he did. And keep in mind, this was an 11, 12-year-old boy that was able to come up with this. He said, all right, I know that this is equal to a certain sum. So he said S equals 1 plus 2 plus 3 plus all the way to 100. And he noticed that if you took the first and last terms there, added them together, you get 101. Then he said, all right, if you take these two terms and add them together there, you get 101. If you get those two terms there, add them together, you get 101. So every pair of terms added like this gave the same sum of 101. So we thought to rewrite this going backwards. Like this. So you said, all right, what is this going to be? If we added this now, we have 2s equals 101 plus 101 plus 101 plus, and then over here, 101, 101 plus 101. So we said, well, there are 100 of these sums here. So it's 100 times 101 is equal to 2s. So 2s is equal to 10,100, where the sum is equal to 5,050. Took them just a couple seconds to figure out what the teacher thought would take them a little bit of time to add 100 numbers together by hand. And thus a new formula was born, the formula for the partial sum of an arithmetic sequence. Now this only works if the sequence is arithmetic. It's what we've been studying the last few minutes. Arithmetic sequences, remember, is when we have a common difference between terms. And if you notice let's go back a step. Let's go back a step to right here. 2s equals 100 times 101. What we need to do now is generalize this to work in any situation. So what's the significance of these two values? Well, 100 here, this is the number of terms that are being added. This value here, remember, was the first term plus the last term, a sub n, where n is the number of terms being added. So I'm going to say number of terms n, and then all we got to do is divide it by 2. So s is equal to the number of terms being added multiplied by the sum of the first term plus the last term, all divided by 2. And that is our formula created by a young 11-year-old schoolboy for the partial sum of an arithmetic sequence. So what we need to do then is practice using this partial sum of an arithmetic sequence formula, because this is the next part of your homework. I've got 3 different examples here of how you're going to evaluate a partial sum. It may be written in sigma notation, like part C here. We may have a portion of the sequence written out, like part B, or it may be a little more clearly spelled out, like in part A. We know the first term, the common difference, and the number of terms we're adding. So these are 3 different instances of how you're going to see these problems in your homework or on an exam. But they all are going to use this formula right here for the partial sum of an arithmetic sequence. So let's start with part A. The sum of the first 30 terms is going to be the number of terms that we're adding together, which is 30, and then we're going to multiply that by the sum of the first term. We don't know the last term there. So we knew that we were adding 30 terms together, and they gave us the first term, which was 10, but what they didn't give us was the 30th term. But we do have a common difference right here. D equals -8. So what we need to do to find that 30th term is to generate a quick explicit or nth term formula. So we could do it one of 2 ways. I've shown you 2 different ways already to generate the nth term. The very first way was a sub n is equal to the first term plus n minus 1 times the common difference. We could do it that way. Or the other way was to say, well, it's an arithmetic sequence, so it's going to resemble a linear function, mx plus b, slope-intercept form, where the common difference is like your slope, and then this term here is kind of like your y-intercept, or the term in front of the first term. So if the first term is 10 and the common difference is -8, then if there were a term in front of that first term, it would be 18. So this is our explicit formula for this sequence. Now to find the 30th term, we would just plug in 30. So -8 times 30 plus 18, that's -240 plus 18. So -240 plus 18 is -222. So that's our 30th term. That's going to go right here. And then we continue to evaluate this formula. 30, and then 10 plus -222 is 212 divided by 2. This is where we would now get a calculator to figure out the rest of this. We get negative 3,180. So the sum of the first 30 terms of this sequence right here, negative 8n plus 18, the sum of the first 30 terms will be negative 3,180. Now, let's figure out what we're missing on part B. We know the first term, we know the last term, we know the common difference, what we don't know, so I'm just thinking about this formula, what we don't know is how many terms we're adding. I've only written 1, 2, 3, 4. I've written 4 terms, but there's a whole number of terms not written there. So the question is, how many terms is that? So yet again, it would be helpful to consider the nth term formula for this sequence. So we know that the common difference is negative 4. And if there was a term in front of this first term here, it would be 93. So there's our nth term. Now, what I'm trying to figure out is, what term is 13? Is it the 20th term? Is it the 40th term? 13 is an a sub n value. What I'm trying to figure out is what is its n value. So I could solve that equation by plugging in 13 for a sub n, and then solving for n to figure out its n value, meaning what spot it is in the sequence. So if I solve this equation now, and then divide 80 by 4, we get n equals 20, meaning this is the 20th. This term right here is the 20th term in the sequence. So now we know that 13 is the 20th term. So we have the information we need to use the formula. The sum of the first 20 terms then is 20 times the first term plus the last term written, which is 13, over 2. And then 89 plus 13 is 102. So that's 10 times 102, or 1020. Okay. Part C, it's given in sigma notation. So we have to be a little careful. They're playing a mean trick on us. Right there when n equals 0, it's gonna, you gotta kind of pause and think about what that means. If we start with an n value of 0 and end with an n value of 1, we're actually, or sorry, with an n value of 20, we're actually adding 21 terms. So we're adding 21 terms. We need to know the first term, and we need to know what this term here would be. Which would actually be the 21st term in the sequence. So maybe to illustrate this a little better, if we were to write out a couple of terms in this sequence, we start with an n value of 0. So you plug in a 0 there. 1 minus 2 times 0 is 1. Now you increase the value of n, so now n is going to equal 1. 1 minus 2 times 1 is negative 1. Now we increase the value of n to 2, so 1 minus 2 times 2 is negative 3. Now we increase it n to 3. 1 minus 2 times 3 is negative 5. So there's a couple of terms in the sequence. 1 plus negative 1 plus negative 3 plus negative 5 plus all the way. Now we end with an n value of 20. So 1 minus 2 times 20 is negative 39. So this would be the first term. This would be the 21st term. So we can figure out the sum now. We're adding 21 terms. First term is 1. 21st term is negative 39. We divide that by 2. So 21 times negative 38 divided by 2. So we plug this into a calculator, and we would get negative 399. So we've covered now how to use this formula created by Carl Friedrich Gauss to find the partial sum of an arithmetic sequence, written a various number of ways. So part A, we had some information given about the sequence. We didn't know what that 30th term was, so we had to use the nth term formula to find that 30th term. For part B, we had some of the sequence written out. We just didn't know how many terms were actually written out, so we had to use again the nth term formula, or the explicit formula, to find out what particular spot the value of 13 was in, and it was the 20 spot. And then for part C, it was already given in sigma notation. They threw a little bit of a curveball because it started with n equals 0, which means that there were actually 21 terms we were adding together. But that should finish up now lesson 8.2.